So, where I in fact left you in the last lecture was with the definition of speed. An average speed, which is defined as the change in the value of x upon the change in the value of t, x2 minus x1, t2 minus t1, where this is the start of the event 1 and this is the final values for the event where the measurement has been done. So the total distance divided by the total time, and this turns out to be in naturally meter per second. In the international units or system international, the speed turns out to be like that. Now, as I told you, just kind of introduced you what is the vector counterpart of speed. I said that the velocity v, which is, I'll write like this. This is how any vector is indicated. Velocity v is equal to v, the magnitude of the velocity, or I'll say it's like this, into v cap. This is a cap vector, which is a unit vector for the velocity. The direction of this vector and this unit vector is one and the same. This is the magnitude, and this magnitude I can write as simply as v, which is the measure of the speed, and v cap. So in the same way, I will now write that the definition of velocity. I'll say that my velocity v is equal to naturally the vector delta x upon delta t. Whereas x, velocity or acceleration, force and many other things, they are vector quantities. Time and mass, they are scalars. Right now we will consider them to be scalars, so they have only a magnitude, because it doesn't make sense that time in the x direction and time in the y direction and time upwards and time downwards. No, they don't have different meanings. So time is the same in all directions, and whereas these things are about the function of the quantity. So now this again the same way. This is x2 the vector minus x1 the vector, t2 the time minus t1 the time. And this I can write if the value of the time is very small, that is in the limit. I can write this as in the limit. In the limit means under the condition, under the constraint that my delta t is very infinitesimally small, or it tends to 0. This will become equal to delta x upon delta t, and which we can write in the language of calculus as ddt rate of change of x with respect to time t. So this becomes dx upon dt. Okay, so this is the derivative, and the derivative with respect to t is often defined as x dot, often x dot, where we understand that we say with space also, we understand that this is dx dt are the first derivative. Okay, and similarly we can have second derivative and third derivative, and number of dots keeps on increasing. So the velocity now we define as the rate of change of displacement with time. This velocity we can say that this is an instantaneous velocity. What is this? This is instantaneous velocity. Instantaneous velocity. Any velocity at a given time. Instantaneous velocity. So the instantaneous velocity is dx upon dt, rate of change of x with time. Yeah, time rate of change of displacement. Time rate of change of displacement, which is the vector displacement. Now I'll just give you an example about this displacement. Suppose we start at a time t is equal to 0 at a point A, and we move along the x-axis like this to a point, I mark it B, and maybe this is from here to here, the distance is 100 meters. Okay, thereafter, and I take a total time of 10 seconds. Okay, and while I move from A to B, my average velocity does not change, which means my instantaneous velocity also does not change from A to B. But while I reach B, what I do is I again momentarily stop for a moment, and then I go back with the same speed and arrive at the point A. So look here, in the first case, from A to B, the displacement is 100 meters in this direction, say the x-axis, and later from B to A, the displacement is in this direction. Now if I add up the displacements, so what will happen? This is interesting, that the displacement here in the second case, where I go from A to B and travel back to A, the final position is the same as the initial position, and therefore when I look at the delta x value, then x1 is the same as x2. Both in this case appear to be 0, and so the total displacement that I have is 0. and total time that is taken is plus another 10 seconds to come back. So 10 seconds in this direction. So I can say that the velocity, if I measure the average velocity, V average will be equal to XA minus XA. XA minus XA, which is equal to, you can write it as 0 minus 0 upon the total time. And the total time is 10 second plus 10 second. So this is 0 minus 0 and divided by 20 seconds. So 0 meters divided by 20 seconds, and this is easily understood as equal to 0 meter per second. So boys and girls, in their initial stages also they can understand that the velocity in this case, the average velocity in this case has been equal to 0. But the average speed, that is 100 plus 100 divided by 10 second plus 10 second, so it will be equal to 10 meters per second. So this is the distinction that we have. So there is an average velocity and there is an instantaneous velocity. So for example, okay, I'll not elaborate that, but instead I will go and the instantaneous velocity that we have, what we can do is that we can introduce what is known as acceleration, which I introduced before also. Acceleration is obtained normally with an application of force, but acceleration in the kinematics, this is defined as the rate of change of velocity. Okay, so average acceleration in the first instance is equal to A average is equal to the velocity at the end of the interval, V2 minus V1. Here we will take the two velocities in the same direction. Okay, so only the magnitudes have to be taken. T2 minus T1, etc. This I can say that this is delta V, the change in the value of V upon the change in the value of T. And then if this delta T under any situation, this is very, very small, so I can write from here, we can go like this, limit again delta T tends to 0, delta V upon delta T, and this becomes equal to what I have already defined as dV. So we have defined the acceleration, average acceleration, as A average, the final velocity minus the initial velocity, the final time minus the initial time, delta V upon delta T, and in the limit, the delta T tends to 0, I can write it dV, delta V upon delta T is equal to dV dt, which is actually the V2 minus V1 upon T2 minus T1 meter per second square. Meter per second for here and time second here, so this is meter per second square. Now if I write the equation in terms of the vector acceleration, then I will write limit delta T tends to 0, delta V upon delta T, and dV dt vector v, which I can write as ddt of dx from here, dx upon dt, the velocity that was defined earlier, the instantaneous velocity, and this becomes d2x upon dt, 2 meter per second square. Remember, what I said was, I wrote here that d2x upon dt2. See, I'm going to call it again, this expression as the second order derivative of x, that I have differentiated x with respect to time and thereafter again with respect to time, and I call it d2x upon dt2. Not like this, that d square x upon dt square. No. No d square here and no t square over here. The d2x upon dt2 is the acceleration that we have, like this. Now, as I told you that I will derive this set of equations, and I consider it essential that a student should be able to derive these expressions at the drop of a hat. Derive it with all the constraints in his or her mind. Because this set of equations, v is equal to u plus at, s is equal to ut plus half at square, v square is equal to u square plus 2as, they appear to be very musical. And because we use time and again, recall these equations, so, and their utterance being very musical, बड़ा अच्छा लगता है, मधुर लगता है कानों को, इसलिए ये सब याद हो जाते हैं. इसलिए बहुत से लोग कहते हैं कि अरे साहब ये इक्वेशन ही तो है, ये इक्वेशन हम याद कर लेंगे. लेकिन फ़ायदा क्या हुआ जब तक आप समझेंगे नहीं कि इसकी बाउंड्री कंडीशंस क्या हैं, व्हाट आर देयर बाउंड्री कंडीशंस and how these equations have been derived, what the symbols mean, and just like that, because in any equation the unit of every term that is there must be the same, like here also, but we teachers show you a magic that the distance covered in the nth second, and that you are not able to say why one is meters, the other is meter per second, and the other is meter per second square. The terms are different. Okay. So with this, what is this? This is not the kinetics. This is the kinematics, where only the two dimensions out of the three fundamentals, the two things which have been taken are the displacement and the time. And time rate of change of displacement, time rate of change of displacement. So we have now acceleration and the velocity as also the displacement, and they are related like this. These relations I will derive for you, and I hope that when I derive it for you, you will enjoy that. So my criterion, in the beginning I told you that I want you to enjoy your physics, enjoy your learning, and thereafter I'll take up some things associated with that, because here the value of A is a constant. So here the value of A is such that with time the value of A does not change. So I will show it on the XY graph. The value of A will remain constant. it will not change. I'll show you how the velocity goes, how the other things go with the help of the graphs, the xy curve, where this is the relation, and one of the examples from there I will take, and I will relate to what is small g, that is the free fall of bodies. And right now I am asking you, if I have, suppose this pen I push like this, okay, so I am asking you a question, ponder, think, okay, probe. If during this motion, when the velocity of the body is going small and small and small, is the body falling or not? Number two, when it stops at a certain height, at a certain time, is the body falling or not? And when of course it is falling, then the body is falling or not. So that's a very interesting situation. The situation of free fall with help of the acceleration due to gravity, which we will consider does not change with the height or during the fall, because it changes if the height that we go is quite there. So for today, remember, I still want you to come back to this lecture, the next lecture. Before that, be prepared about these equations, okay? And if you will later on enjoy the derivation of these equations with the help of the logic that we have, I will also feel happy and enjoy that I had an interaction with you. Hope that I have been able to deliver, and I'll be able to deliver tomorrow and after and after and after. Give us your feedback and ask your questions so that, and be a critic. Because in the beginning, in the first lecture, I said that 80% of what I know is from my students. And since you are pondering over here, since you are doing the business of learning physics, so therefore you qualify to be my students, and therefore you must have the courage to ask me probing questions. Try to fail me, and I will be very happy. Thank you very much for today.